Okay, class, today we are talking about biconditional statements in lecture 5 on Intro to Proofs. So these are just another kind of statement that we can study. So we already studied conditional statements. We should think that these are related, and they are. A biconditional statement is very much like a conditional statement. It's one of the form. So a conditional statement is of the form if P, then Q. But a biconditional statement means that not only does P imply Q, so whenever P happens, Q happens, but also and if Q happens, then P happens. So in English, we don't really use parentheses, but you should really think about it like this. So if something happens, then something else happens, and vice versa. So we can write this symbolically using operators. P implies Q, written like that, and Q implies P. So then later we can think about it using truth tables, which we'll get to. But first, we'll do some examples and stuff and also see other notation. So you can also write this in a couple different ways. So one very standard thing is to write an arrow going back and forth between P and Q. So that's just saying if then goes both ways. But if you want to use sentences, people write this, if and only if. But some people get confused by that. It really just means if then in both directions again, just said in a fancy way. And if you're too lazy to do that, but you also don't like arrows for some reason, then you can write P-I-F-F-Q, and that means if and only if. So a couple different ways to write the same thing. But the main point, or the idea, is that P and Q both imply each other. Okay? When one happens, or when one is true, so is the other. And then one more thing you can say, and this will come up in the next lecture. In such a case, you can say P and Q are logically equivalent or just equivalent. So what does that mean? That means that they're really just saying the same thing. P and Q are saying the same thing, although maybe in a different way. They are both statements imparting the same knowledge or fact, but they're said perhaps differently, so you can't tell immediately that they are equivalent. And so the way you can tell that they are equivalent is because they happen to imply each other. So here's an example of such a thing, a mathy example that you may have heard of before. So a triangle is equilateral. Equilateral, I think that's how you spell it. If and only if, meaning it's equivalent to saying that the triangle has all three 60-degree angles. So equilateral means what? It means they all have the same side lengths. And that turns out to be exactly the same as having all three angles be the exact same number, which would have to be 60 because 180 divided by 3 is 60. So here, this is P, and this is Q. And we're not going to do this proof because we don't have enough geometry background in the back of our minds out of nowhere just to remember all this stuff. But hopefully this is a fact you have seen before, that yes, if a triangle has all three sides the same, then the angles have to all be the same too, which means they all have to be 60. And so when one happens, the other happens. So if you have three sides the same, you'll automatically have three angles the same. But also, if you have three angles the same, you'll automatically have the three side lengths the same. So they do imply each other. Okay, so it's also good to see non-examples. Those are much easier to find than examples. So if I let P be, I win the lottery, and I let Q be, I am wealthy, well, if you win the lottery, it does follow that you must be wealthy automatically. So this part is true. But just because you are wealthy doesn't mean your wealth came from the lottery. It doesn't mean you'll win the lottery as a result. So this is false. So this guy is false. They do not imply each other. They are not saying the same thing in two different ways. One implies the other, but not vice versa. So thinking of examples is hard when you're just trying to not use math. So here's a really dumb example, but it works. So I drank the water is exactly the same as saying the water was drank by me. Drunk by me? Drunken? I don't know. Not an English class, I guess. This is true. If I drink the water, then it is true that the water was drank by me and vice versa. So this is true. So to be true, both directions got to be true. One has to imply the other and also the other way. So let's do a more mathy example of something false. X is a positive number if and only if x squared is positive. So this one is false because although P does imply Q, if you consider this part to be P and this part to be Q, so although that's true, this is false. I guess I should say even though this is true, the reverse is false, right? So if x is a positive number, then yes, when you square it, it will be positive. But if you start off with x squared being a positive number, you could still have x be a negative number. So that's why Q implies P is false. Okay, so these two facts are not equivalent. That means you're not saying the same thing in two different ways. You are saying two different things. And one does imply the other, but not vice versa. Okay, so now let's create the truth table for this thing. So you can create the truth table for the biconditional, the if and only if, and then you can think of it sort of as a logical operator. So you're taking two statements and you're creating the statement one if and only if the other, and then we're seeing with a truth table when is that guy true, when is that mu statement true or false. So before we write it down, let's think about what we should get. So when should this be true? Well, for this to be true, that means that P and Q are exactly the same statement, but maybe said differently. So they're like secretly the same. Maybe not so secretly. Maybe you can tell right away that they're the same. But the point is that they are the same. So they should imply each other. That statement should be true if they are true at the same time, but also if they're false at the same time. So because they are the same statement. So this should be true when P and Q are true, and also true when P and Q are false. Because if P and Q are secretly saying the same thing, then they should be false together. They should both be wrong together, just like they should both be right together. But when one is true, the other can't be false because they're supposed to be the same thing, and vice versa. So in those situations, the truth table is going to reveal that it's false. Okay, so let's see that happens. So the truth table relies on P and Q. So that means I gotta do all 4 possibilities again of what can happen if I have 2 statements. So they can both be true, one can be false, the other can be false, or they can both be false. And then to make the truth table for this guy, I gotta remember what it really was. It was really P implies Q and Q implies P. So I have to build this thing up in pieces, which means I have to write down the truth table for P implies Q. Then I also need the truth table for Q implies P. And then I can write down the truth table for the AND of the 2 statements. And that'll be the final truth table I'm after. Okay, so when is P implies Q true? That's true if they're both true, or if the hypothesis is true, it's automatically true. It's only false if the hypothesis is true, but then the conclusion doesn't follow. Okay, so then Q implies P is just the same thing in reverse. So they're both true, that's fine. If the hypothesis, which is now Q, is true, then it's automatically true. So this is true, whoops. But if the hypothesis is true, but then the conclusion is false, which is happening right here, then, why do I keep writing the wrong thing down? Then it's false. And lastly here, the hypothesis is false again, so it's automatically true. Okay, so how do AND statements work? When is an AND statement true? It's true if both pieces are true. So in this situation, both pieces are true. But here, only one is true, and here only one is true as well. So those are both going to be false. And that's exactly what we were after, because we were saying that if Q and P are to be exactly the same statement, but said differently, then they can't have one be true and the other be false. That would mean that they don't imply each other because they're not saying the same thing. Okay, and then lastly, if they're both P and Q are false, then that should also be okay. And it turns out to be okay because both of the implications are true down there. So what we're really worried about is over here. So I'll draw these in green. The middle piece, this is just like the building. But what we're really saying is P if and only if Q is true when both P and Q are true, P and Q are true, but also true if they're both false. Because they are the same statement, they should be true together and they should be false together. And if one is true and the other is false, that's when you should get false for the entirety of the biconditional. Okay. All right, now let's do a proof. We always want to be proven in this class. So we can do one now. So to prove a biconditional statement, well, we're just breaking down what we just did. We have to prove 2 things. We prove this happens, that P implies Q, and that Q implies P. So it's just 2 proofs in one instead of, there's no like new special technique, it's just 2 different proofs. Okay, so here's a good statement to practice with. X is odd is exactly the same as saying that X plus 1 is even. These are the same fact, said differently. And so to prove this, we have to do what I just said. We have to show P implies Q and Q implies P. And so because what's going on is it's really two different proofs. What people write in the proof is they just write a little arrow, but for some reason they like to use the double arrow in the proof. They write this to say, I'm going to show P implies Q right now. And then later, when they're done with that, they draw an arrow the other way and they say, okay, now I'm going to show Q implies P. So that's the notation. But then as far as each individual proof, there's nothing special. It's just the same as proving other things. Okay, so let's do this direction first. So this means that I'm assuming P, and I'm going to try to prove that Q follows as a result. So we've done proofs like this before. So I have to let the assumption be true. Let X be an odd number. And then I'm going to show or say what I want to do. We will prove that X plus 1 is even as a result of X being odd. Okay, so how will we do that? So remember how proofs always work, for now at least. You're just really expanding upon things. So what does it mean for X to be an odd number? Well, it secretly means that it looks like 2n plus 1, where n is an integer. So then, once I have X, I'll be able to study what X plus 1 looks like. It just looks like the same thing, plus 1. And then I have to think about, why is that an even number? Well, it's because I can factor a 2 out, and now it looks like 2 times something. So that's how the proof is going to go. That's the scratch work. All right, so why can I do that? Since X is odd, I can just say something else about it. I can say that it equals 2n plus 1 for some integer n. Then, because it looks like that, I can do something else. I can talk about X plus 1. It's just the same thing, but plus 1. And now I just do a little bit of algebra to see why this is even. Why is this even? Because when I combine those ones together, I'm now able to factor out a 2. And it looks like 2 times a number, 2 times an integer specifically. So I've shown that X plus 1 is even. Okay, so that proves, this proves P implies Q. We don't have to really say this sentence, so I'll put it as a parenthetical. But that's basically the end of that direction of the proof. So now what we do is we say, okay, I'm going to prove the reverse direction. I'm going to indicate that I'm doing that by drawing the arrows backwards. So now I'm trying to say that if X plus 1 is even, that means X is odd automatically. So I have to assume that the new hypothesis, which is Q, so I have to let X plus 1 be an odd number. And then I'll just say what I'm going to do. Show X is an even number. And it's going to work the same. So maybe some scratch work over here. What does it really mean for X plus 1 to be odd? It really means X plus 1 looks like 2 times a number plus 1. So then why is X even? Well, if I just subtract the 1, now I get hopefully a very clear even number. 2 times a number is an even number. So that's exactly how the proof is going to go. So since X plus 1 is odd, I can say X plus 1 equals 2 times a number plus 1 for some integer. And then I can continue. I can now study X by just subtracting 1 over. So X is even. because it's 2 times the number. Okay, so that's the end of the proof. I've now shown 2 things. Then it's basically just 2 proofs in one. I've shown P implies Q and Q implies P. So I've shown that these are logically equivalent statements, that they are secretly the same thing. If one happens, the other happens, and vice versa. They're both true at the same time. They're both false at the same time. You can say the same thing in many different ways. So next time, we're going to study something very similar. We look at logically equivalent statements, which is basically what we just did, except we're going to do it in a more fancy way. So right now, this means that they are equivalent. But what we want to look at is when we have more complicated things. So we'll see something like this. So for example, I'm allowed to combine all my logical operators. So if I do something like this, it'll turn out to be the same as something else. And I'll just give it away, but next time we'll see why. But these 2 statements are logically equivalent. So the idea right now is you're given 2 specific statements, like x is odd and x plus 1 is even or something. You're given 2 specific statements, and you want to see if they're logically equivalent by proving that they imply each other. Whereas here, you're not given 2 specific statements. You're given 2 general logical statements. So P and Q here could be whatever you want, and this equivalence will always be true. So it's an equivalence of 2 statements formed by using logical operators, versus here is just an equivalence of 2 statements that could seem related or unrelated. And that's going to be the difference. Okay, so next time we'll see how to talk about this stuff. Okay, see you later.